Hello, my dear students, and welcome to our lecture screencast for Chapter 6, accompanied by a few short questions and some practice. I'll try to not follow the traditional mold in teaching this material because it's often taught poorly or incorrectly and involves a little physics and goes, I won't say on tangents, but brings in different information from different places, math and physics especially, but also electricity and electronics, which is physics as well. And I think it's because people try to oversimplify it, or people don't understand it, or don't understand it well when they teach it. And I'm not sure how well I understand it. I'm not a good physical chemist, but I'm a fair biophysicist, and I do appreciate the importance for understanding the electronic structure of the atom because we need to describe what electrons are doing in atoms and molecules and understand something about the energies involved to understand bonding and how these molecules come together and how they also subsequently fall apart and rearrange themselves. In other words, we need this information to understand chemicals and to understand the reactions that they undergo. And we're going to cover this because the next chapter is super important, because knowing how to use effectively a periodic table, and I don't know who you might have had in the past, but I don't mean memorizing it, but knowing how to use it as a tool is arguably the most important skill you should acquire as you work through an understanding of chemistry. So we've established that this atom has a nucleus composed of protons and electrons and electrons spinning around somewhere between 1 and 118 electrons, because there are 118 elements in that periodic table. That's a lot of spinning electrons, all with a negative charge, that have to be accommodated in a very small space. And I would maybe grossly oversimplify this chapter by saying that is where we're going. We're trying to explain how you put and fit all these electrons together. Also, another or better question is, what are all these electrons doing, and how do you get 118 electrons spinning around this nucleus without bumping into each other? And we're going to hopefully leave you with a little clearer idea of the atom, the structure of the atom, the electronic structure of the atom. And I wish we could do some demos and some labs. Anything from heating up a metal loop or metal wire from a toaster or in a furnace, or a blacksmith getting his metal red hot, yellow hot, white hot, and exciting electrons different ways in spectrum tubes or ordinary incandescent or fluorescent, and now LED lights. All of those phenomena are explained by the electronic structure of the atom. So we have to talk a little bit about waves because of the dual nature of these electrons. And, a wave is a periodic oscillation and a way to transmit energy and information through space. Not matter, but energy, at least, and subsequently information through space. And when we draw a wave, this is a wave like an ocean wave here, but most often we draw these as sine waves. Let me do this so that I can use my pencil. Regular up and down sine waves, more regular than what I've drawn. And we have crests, and depending on which way you're looking at it, troughs. And the distance between waves is the wavelength. And we designate that with the Greek letter lambda, a lowercase lambda. And all this is distance between corresponding points. It could be the distance between the troughs or any point, the midpoint on the side going down in each one. And that wavelength tells us a bit about the wave. And that wavelength is proportional, actually inversely proportional to the frequency, which in chemistry we don't call F, we call it with this funny looking V. I can't draw it because my hand is moving at the same time I'm pressing on my iPad here, but the frequency is how many times this wavelength passes the observer in a given amount of time, usually a second. And it's going to be so many per second or reciprocal seconds. We also call those units hertz, named after Mr. Hertz, so I tend to use a capital H. This one, if this is 1 second, this one comes by 2 times. And its frequency, or this value nu, Greek letter nu, that, lowercase nu, that wave in part A has a frequency of 2 per second. If this period that we're observing this is 1 second. And here's one that comes by 1, 2, 3, 4 times in 1 second. So it has a frequency of 4 per second. See, to the -1. So we can write this per second, second to the -1, 1 over second, however you want to depict it. And again, this is in hertz. Now, these two values, the wavelength and the frequency, are related because they're related to the speed, which is a constant, which we'll abbreviate C in our case for an electromagnetic wave. In other words, a light radio wave, something on the electromagnetic spectrum. It's also true for sound waves, ocean waves, any kind of wave, but we reserve this value C for constant for the speed of light, which all these X-rays, gamma rays, microwaves, radio waves, including CB, shortwave, television, radio frequencies, radar frequencies, all of these travel at the speed of light, which is 3 times 10 to the 10th centimeters per second. Or as your book puts it, 3 times 10 to the 8th meters per second. And light has this, the visible light we see is a form of this kind of electromagnetic radiation, ranging from violet to red. You probably learned the colors in the opposite order: red, orange, yellow, green, blue, indigo, violet. with the funny man's name, Roy G. Biv. Anyway, this velocity, our wave speed, relates the wavelength to the frequency. And you can see they're proportional, inversely proportional. If my frequency goes up, my wavelength has to go down to maintain the same speed. That's all. That's all I want you to know. But more important than the relationship between wavelength and frequency for our discussion is another equation, and that is one that relates the energies of these different wavelengths, relate specifically, usually the frequency, to the amount of energy they carry. You know that red light is long wavelength, low energy, and violet, especially ultraviolet, is short wavelength, high energy, because you can get sunburned by it, right? And an X-ray can pass through your body. Okay? But infrared can carry energy and can heat things up, but not like, for example, an X-ray or a gamma ray, which will pass through the entire Earth. So, I don't know that I would have phrased this quite this way, but the models of the atom we've discussed so far do not explain why, when I heat certain elements, metals especially, they glow. What's happening when they glow? Well, to put it simply, the electrons in their orbits about the nucleus, these electrons going around, don't think of them as in planetary orbits in a flat sphere. We're going to discuss their shapes in a minute. Remember, this is three-dimensional. I'm just not able to draw a atom in 3 dimensions. But these electrons in their orbits can actually absorb energy. In this case, in this example of iron, they absorb the electrons, absorb energy, and are promoted to a higher energy level. And they don't naturally exist there. This is their normal, what we call ground state. But it absorbs some energy and can exist in an excited state. We're exciting this electron. We can excite it chemically, we can excite it with chemiluminescence, we can excite it with heat, thermally, we can excite it with electricity, we can even excite it with pressure and friction in triboluminescence, which normally we would be doing an experiment on chemiluminescence and light sticks and factors affecting the rate of reaction. Triboluminescence, which I demonstrate with wintergreen lifesavers, believe it or not, fluorescence and incandescence, where we excite electrons in different molecules with either an electric current or heat, or by absorbing energy from another electron in the form of light. So it doesn't matter how you excite it. If you excite it, it will be raised to a higher energy state, and it will decay back down because it doesn't belong there. It's more comfortable down here. And when it does that, it sheds that excess energy as heat and light. Okay? Sorry, this is energy. So, Max Planck was studying this and saw that, you know what? Some things if I may move ahead, like neon or hydrogen, when their electrons get promoted to a higher energy level and they decay, they emit light of a very specific wavelength. We all know the color of neon. Hydrogen has only certain allowable wavelengths when it gets excited that it will emit. It doesn't emit a continuous spectrum, it emits what we call a line spectrum. So, if we look at hydrogen, I'm trying to see, I don't know which element these are. Okay, here's hydrogen. It only emits light at these frequencies and nothing in between. It only emits lights at very specific frequencies. Hydrogen is element number 1. It has 1 electron. Helium is element number 2. It has 2 electrons. Neon is element number 10. I don't have a periodic table in front of me, but it has a larger number of electrons. Okay? So, that neon has lots of electrons that can make all kinds of different energy transitions. Not only that, they may start at different levels because the different electrons in neon are already at different levels. And so it can emit more and different kinds of light. Only certain allowable transitions will be observed in hydrogen. But here's the point that Max Planck saw. We can look at an incandescent bulb, which is excited metal like iron, that will eventually not just glow red hot, but if you add more energy, yellow hot, and even more energy, white hot. And as we put more energy in, we're exciting more and different electrons to more and different energy states so that we get all kinds of transitions and wavelengths being produced that combine to form white light. Because you know white light is made up of all different colors. You know that because if you put white light through a prism, you can separate those colors out. Now, he saw that energy comes in quanta, that those energy transitions are not continuous. I add energy and I get more and more and more and more excited. No, I add energy, and when I absorb enough, I get excited to the next level. And add more, and I get excited to the next level. And I get excited to higher and higher levels. But I can't exist between levels if I'm an electron. I'm at one level or another. And when I fall down or go down the steps, whether I go down 1 or 5 or 6 levels, 2, 3, 4 or more levels, that corresponds to a very specific amount of energy, and therefore we can relate this using simple math. Well, I won't say simple math, but straightforward math. These correspond to very specific wavelengths because they correspond to very specific energy transitions, because back in the atom, those electrons are making very specific adjustments in their orbits. They're going from one orbit to the next, and they're not in between. So we can't put on our Superman glasses and look at the electrons to see what they're doing. But what we can do is see how these are behaving. And Einstein was looking at different metals to see how they behave in what's called the photoelectric effect. This is how solar cells and light detectors used in burglar alarms, where you break the light beam, for example. And you break the light beam and you shut off the current, which can itself be detected. If you shine light on the surface of certain metals, you can produce a current. You can excite those electrons in the metal, and if you excite them enough, they will actually leave the metal and produce a current and flow. Okay? The electrons will be emitted. But they only do that at a very specific wavelength, a very specific color, which means they do so only at a very specific frequency. And we can relate that frequency, Dunbar, to the energy. And he saw that everything is proportional with the frequency is proportional to the energy and is related to it through this constant called Planck's constant. And actually, this is what Einstein got his Nobel Prize for. So, again, when we excite these gases, and you can do all different kinds of elements in here. I like to do mercury and a few others. When you put them, this is basically a neon light. We put a current across here, and actually it's an alternating current, so it shouldn't have plus and minus, but you put a current across here and excite those electrons in this vacuum tube. This is a vacuum tube, a glass tube with a small amount of atoms of hydrogen or neon, hydrogen here, neon here, that get excited by the electricity and jump up. They take that energy, absorb that energy, jump up to a higher orbital. That promotes them up to a higher orbital, and they can fall back down. But like we said, they do it stepwise, producing a line spectrum, as opposed to a continuous spectrum you see in a rainbow or in a normal incandescent light. Fluorescent lights are kind of in between a line spectrum and a continuous spectrum. They have broad bands of light that gets combined to form various shades of white light. I'm not sure shades is a proper term. Like the difference between a stadium light and a stage light and sunlight. It's all white light, but we see some differences in them. So, based upon how much of the different colors are added together. Now, you can analyze these line spectra, especially for hydrogen, because it's relatively simple, depending on whether you're looking in the visible with its 4 lines or the ultraviolet and infrared off to the, I'm sorry, I didn't mean to do that, off to the 2 sides of this spectrum. These are the wavelengths, 700 nanometers. That's the distance between waves in the red, 600, 660, and 400, and below 340 is ultraviolet. So people have studied these lines, calculated the energy contained in those lines, and shown that they correspond to very specific energy transition. Here's an electron at its first energy level. It goes up to the second energy level, and when it falls back down, okay, it produces the red line, this line right here, okay? And if I go up higher, for example, to this one, now I have two transitions I can do. I can go down one step, or I can go down two steps and emit different wavelengths of light. That given, it may not even be visible, maybe in the infrared or ultraviolet as well, and they can give you, from that wavelength, the frequency, and from the frequency, the energy. Actually, one or the other will work. So, um, the point is, we can calculate the energy contained, and it's always in a stepwise fashion. People like to compare it to climbing a ladder. You can't, you're either on this level or this one. You know, your feet can't be in between or going up the stairs. One thing I do want to emphasize, though, is that these rungs on the ladder are not equally spaced. As we go up the ladder, they get closer and closer together, like this over here in the diagram. So all this may seem very complicated to you, but what I want you to know is that the energy, the electrons exist at very specific energy levels, and there are only certain allowed energies. You can't be between energy levels. And we can relate the light that's emitted when we excite them, technically the spectral lines in a line spectrum, to the energy of those levels. This is that equation to calculate energy from the frequency, nu, and Planck's constant. So, here you see 1, 2, 3, 4, 5 lines. 1, 2, 3, 4. I believe these are the 4 visible spectrum ones. So, you know, some in the UV, some in the infrared, and 4 in the visible. And 1, 2, 3. So you can get these different energy transitions. You can go to level 1 and fall back down, level 2 and fall all the way back down, level 3 and fall all the way back down, 4 and 5. You can see them getting closer. The important thing is the previous models we discussed of the atom were not sufficient to explain how the atoms are located in space or why metals glow when you heat them up, and why line spectra are produced by atoms suspended as a gas in a partial vacuum tube called a spectrum tube, and you can separate those spectra out with a device called a spectrometer. And with correct instrumentation, you can even read spectral lines in the infrared and ultraviolet, just depending on your detector. So, we have this new model and we say, wow, that's really cool, except it really only works for hydrogen. It gets very complicated when you get more electrons. And it doesn't, always make sense that you have these electrons out here and a positive charge nucleus down there. There's a couple things about that that don't make sense. All those positive charges packed in together, why aren't they repelling? And we have to go to true quantum atomic physics to explain how they are glued together with all the other subatomic particles, gluons, mesons, muons, etc. And why are those positive charges not repelling each other like they should? But the other thing is, why isn't the positive charge nucleus attracting those electrons to it and having them fall into it? Bohr's model doesn't explain that, and I'm not sure I can either. And the motion is not wave-like in nature, yet it is repeating and does let you make predictions. So, here's what's essential. Electrons exist in certain discrete energy levels. We're going to name them. We're going to number them. And if you transition from one level to another, you need to add energy. Now, de Broglie said that if you can have a photon, which is a wave, but also has a particulate nature, and you have an electron, which is a particle, but has a wave nature, all of these things have that matter should exhibit wave properties, even you or a building or something like that. And there's a relationship here because the bigger you are, the mass is in the denominator, thus, the smaller you're going to make that wavelength, so you're not going to see anything. This is actually your, momentum. That's mass times velocity, right? So, Heisenberg, and we're just going to mention these people because of the contributions they made to our understanding of the atom. This says that our electrons have both a wave and a particulate nature. They behave like waves sometimes when you look at them, and they behave like particles other times. Okay? For example, you can energize electrons and blast them through a sample just like a light wave through a lens. You have to focus them with magnets, but instead of a glass lens, because we're talking different wavelengths outside the visible range, and you can do electron microscopy with them. And because their wavelength is so much smaller, you can see much smaller dimensions, because you can't view anything. I forget, is it half the wavelength? Anyway, the wavelength, lambda, determines your resolution and your ability to distinguish between two closely spaced points. And if you can decrease your wavelength, you can increase the resolution that you're viewing something very small. So electron microscopes don't use light. They use X-rays or electrons, excited electrons that are burned off a filament. So the important thing here is, I don't want to get us bogged down. De Broglie simply stated that, I don't know about simply stated, but our take home is that those electrons have both wave and particulate natures. Heisenberg, studying them, you may know or have heard of the famous Heisenberg uncertainty principle. And this is a problem that if we precisely know where a particle is, we cannot know its momentum, which is related back to its speed. Okay, the change in position x times the change in its momentum, mass times its velocity. You can't know if the certainty in one measurement goes up, the other measurement becomes less certain. There's a joke where Heisenberg is driving from Pine Bluff to Dumas and going past the town I live in. And the cop pulls him over and he says, "Do you know how fast you were going?" And he says, "No, but I know where I am." And if you're being pulled over for speeding between Pine Bluff and Dumas, you're probably in my town of Grady. But the point is, you can either know how fast you're going, or the momentum, the mass, the velocity times the mass, or you can know your location or your position. But the more certainty you have in one, the greater uncertainty you have in the other. You can't know them both with certainty. This brings us to our current model of how those electrons are arranged. They are zooming all over the place, and I wish I could undo that. There should be a way. There we go. That's not it, but there we go. Maybe I can't now. But we now describe these electron orbitals as follows. We do have we use quantum mechanics to describe the relationship between motion of electrons and atoms and their energies. And there is a wave-particle duality that de Broglie was describing. And the wave functions and the mathematical relationships allowed the motion of these electrons and their energies to be described. And because they are quantized, they exist at specific energy levels. They can't go in between energy levels. They are quantized. This is quantum mechanics. And it's very useful for understanding, I guess, the periodic table, or maybe at least appreciating it. And so now we don't depict these as circular orbits or three-dimensional orbits, spherical orbits, but as electron clouds. I'm not sure I can make this bigger. But we describe the position of an electron centered about the nucleus. Oops, okay, I can actually pull that out. But at the origin here, that electron cloud for this one electron, I'm sorry, I did not turn my phone off, but the electron cloud we draw with increasing density where there's a higher probability of finding the electron. Okay? These orbitals are probabilities. And these proper depictions depict electron density, the likelihood or the probability of finding an electron in a given position. You're unlikely to find it out here, and you're more likely to find it in here where it's more densely designated. Okay? We're not going to go into the math. We're not going to work any of those, but we use a set of numbers. Actually, it's not 3, it's 4, because we're going to moved my cursor. We're going to have a fourth one for the electron spin quantum number. So we have 3 numbers, N, L, and M. Okay? This one's quite simple. This is the energy level. 1, 2, 3, 4, 5. L is the shape that electron orbital takes, okay? And we'll just briefly cover each one of them, okay? And then this is how they're arranged within that. So, the principal quantum number corresponds to the energy level. You can't have zero energy, so they're all greater than or equal to 1, and they're integers 1, 2, 3, 4, 5. You could almost say they correspond to the periods in the periodic table. Okay? Those numbers along the left hand side. The other one, the angular momentum quantum number, that helps us discuss and describe the position, are values that range from 0 to n minus 1. So if you have an n, an energy level 1, it can be 0. These are just like giving them a phone number that we can call, because every electron is going to have its own quantum number. Okay? And as a result, our own set of quantum numbers, as a result, no two electrons have the same 3 or 4 quantum numbers. Okay? So these are describing the shapes and types of orbitals. We call our orbitals S, P, D, and F. Okay? And 0, 1, 2, 3, because I can go for, 1, 2, 3, 4. And if I subtract 1, of course I'm going 0, 1, 2, 3. And these are the shapes of our orbitals. And we've got S tend to be spherical. The S doesn't stand for spherical. And that's just a circle I've drawn. The P's tend to be dumbbell shaped and located along the axes. The D's tend to be, although one has a more complex shape, the same dumbbell shape. I've never seen a dumbbell shape like that, but that's the way we describe them, that are also aligned along the plane in space. And the F, they always say, are more complex, so we won't describe them, but I'm going to show you pictures of the F orbitals. They're not that complex. They're just not something you would encounter in geometry. And then the three-dimensional orientation of these orbits. So let's talk about these p orbitals. Okay? I can have a p orbital if I have Cartesian coordinates with x, y, and coming out from the plane z. And I can align some electrons, that electron cloud, along this axis and along the x-axis. Okay, so I have the same thing along the x-axis. Oops, should keep it longer. But, that's my electron cloud. Sometimes it may be out here, but not very often. And along the y-axis. Because what am I doing? These electrons are all negatively charged, and they are also, or are therefore, trying to stay as far apart from one another as they can. There's another thing I haven't told you yet, and that is that each orbital, even a simple s orbital, can only have 2 electrons. So, and these are probably on opposite sides, trying to stay as far apart as they can as they spin around in different ways, but they're always trying to, as efficiently as possible, stay as far apart as possible. And so they would naturally align and describe the axes of a set of three-dimensional Cartesian coordinates. So this is a little confusing. I'm not, you can work this out, okay? This magnetic quantum number describes the three-dimensional orientation that I was just talking about, X, Y, and Z. And the allowed values range from minus, that's not 1, that's an L, to L. Okay? So if our L is 0, 1, 2, 3, this can go from minus 3 to 3. Okay? So as a result, for S, P, D, and F, we can have 1, 3, 5, and 7 different orbitals, or suborbitals, if you will, each with 2 electrons. So this would be 2, 6, 10, and 14. And if you look at the periodic table, you'll see a block of 2. And then over here, you'll have, because there's 2 electrons, you'll have a block of 6. Well, I shouldn't do it like that. You have a block of 2, and over here you have a block of 6. 1, 2, 3, 4, 5, 6. Okay? And then you'll have your D block with 10. And if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there are that's my son's teacher. There are 10 blocks in there. And the only point of this is that no matter what electron configuration you have, everybody has a different quantum number. And if I may go back, my little mnemonic for remembering this is, after many iterations of the Power Rangers, from Dino Force to Mighty Morphin Power Rangers, I've got 10 kids, so I've seen them all. There was one kind of obscure, and probably before your time, that was Space Patrol Delta Force, SPDF Rangers, Power Rangers. So I always think of Power Rangers when I try to remember these. They're very simple. So we have hydrogen with 1 electron. It's just spinning around. But this first shell can accommodate 2. Technically, it's an electron cloud, but we're going to draw it as a circle, or more correctly, as a sphere. And we can have 2 electrons, 1 here and 1 always on the other side. Wherever you draw 1, the other one's probably trying to be as far apart as possible. So hydrogen has 1 electron, and helium has 2 electrons. In the first energy level, that's our N, and then our S spherical shaped type orbital, that's our L, and we don't have to worry about the M, because it can only hold 2. But, so I do hydrogen, helium. What happens when I get to lithium with 3? It can only hold 2. So what do? I put another electron further out and make another sphere. Like they compare this to the nesting Russian dolls. They call this nesting. And then, so this one has 1 S inside it, but then if it's lithium, 1 more electron in its outer shell. So we write lithium 1s2, 2, second energy level. We just expanded and got a bigger one around it because this can only hold 2. So in the second energy level, principal energy level, we have an s orbital with 1 electron in it. And we do that again for beryllium. And at a certain point, these orbitals get so big that not only can we accommodate them out here, we can now also start to accommodate them in some of these p orbitals and have them be far apart. This first one's too small to have anything other than an s orbital because there's no room for any more electrons in or around that. Okay? So we keep going up 1s, 2s, 3s, 4s, 5s, 6s, etc. And we just keep our electrons. Here's some here. And then there's an empty space before we get to the next one, the darker blue. So we have, a small sphere, and then a bigger sphere, and a bigger sphere surrounding it. Those are the nodes. That's all it is. Nodes and antinodes, or period positions of empty space. The p orbitals, like I said, are electron clouds that we depict as these lobe-shaped, sometimes called dumbbell-shaped structures that naturally try to get as far apart from one another as they can, like so. They naturally align along the axes. You can't really say they align, but they're just using space to stay as far apart from one another as they can. The d orbitals now start to put things into the planes instead of along the axes, okay? I can't really draw it, but here it is in this one. And so as we get bigger, we can start to accommodate more electrons in these d orbitals. 4 of the 5 are in the planes. Remember I said there's 10. Well, there's 5 orbitals that can accommodate 10 electrons. The last one is accommodated along one axis with what's called a torus, or a toroidal structure. Not a torus like the Ford Taurus, but a torus, T-O-R-U-S. That's a donut shape. That's the structure of wheels, donuts, wedding rings, all kinds of things in nature. And it's not often taught in geometry because it's not in the standards in Arkansas, despite the fact that you can't describe a Krispy Kreme donut without knowing what a torus is. You take a circle and you rotate it about a central point, and you make a donut. It's a bunch of circles that you could slice. So, what else? Those are the 5 d orbitals. And then they say they're very complicated. The f orbitals are not shown. They are not that complicated. I'm not sure I am hooked up right now, but I did have the d orbitals. Oops, it's not letting me go back. Here are the f orbital shapes. Here, these f orbitals here are, these are the p, okay, and aligned along the 3 axes. Remember that they're all happening together at the same time. Okay. Here are not the ones I want. Here are, let me see if I can find them. Okay, here are the d orbitals, all 5 of them. And those are pretty complicated, but I think I like this picture because you can see they're all following a plane. And you can see how they would kind of nest into one another. Not nest, but but fit and lock into one another. And then the d orbitals themselves are extremely complex, but I don't see why we can't show you them. They look something like this, and there are 7 of them. So, not so complicated that you can say they're not shown or they're too complicated to tell you about. But they are ways that the electrons use to stay as far apart as possible. So, hydrogen has 1 electron. It's easy to depict. We have these electron filling charts that allow us to do what's called the electron configuration of atoms. And that's where we're headed. And that's what's important, and that's all I'm going to ask you in the assignment. Okay? Normally I would do a lab where we would calculate frequencies and energies and look at some spectra, but once again, this is an online course and we're limited in what we can do. I can do a pseudo demonstration lab and have you fill out and write down things, but it's not very satisfying to do it that way. Now, I said there were 4, not the 3 that were originally mentioned in the lecture. And the 4th quantum number is one dealing with spin. The electrons have their own natural spin, and if you have 2 electrons, they must spin in different directions. Okay? They have opposite spins. And that's the quantum number. It's either clockwise or anti-clockwise. So it's that number is either a plus 1/2 or a minus 1/2. These numbers are like phone numbers in the sense that you can give me those 4 numbers and you can say, okay, it's a 2. Okay, that corresponds to the second energy level. The second row in the periodic table, it's a 0. Well, that corresponds to the s orbital, those first 2 rows in the periodic table. Or if you have a 1, the p, and then you have the p that can be aligned along the x, or one that's aligned along the y, or one aligned along the z, each one with their own quantum number designating it. And you can use quantum numbers to specify an electron. So we have this phenomenon, the Pauli exclusion principle. No 2 electrons can have the exactly same energy, so no 2 electrons can have the same quantum number. They must differ by at least one of the 4 values. Okay? And no 2 electrons in the same orbital can't have the same spin unless you play some tricks and do electron spin ESR, electron spin resonance, and look at the energy you have to put in to flip the electrons and make them spin in an opposite direction, for example. We should talk more about spectroscopic techniques, and we will as we go on, and if we had a lab, we would be doing a lot more. So, we have to talk about the actual electron configuration. It's what we've been talking about all along. We're talking about that in the ground state, not one that's excited. And it's a number that tells you the energy level. Then a letter that tells you the type of orbital, S, P, D, or F. And then a superscript that denotes the number of electrons. If you add up all the superscripts, you will get the atomic number, the number of electrons for that element, which should correspond to the number of protons. For example, lithium, element number 3. First two electrons go into the first level, first energy level's s orbital and fill it up. This superscript stands for the electrons. And then we have a 2s and its element number 3, 1. And if I add up all these superscripts, the 2 and the 1, then I get 3, and lithium is atomic number, element number 3. Okay? We have these filling charts, and when we do it, we tend to put arrows. You can actually put arrows too, not just the half arrows. And when you do that, you are denoting the spin. Because like I say, you can only have 2 electrons in any orbital, and they must have opposite spins. So one arrow up, one arrow down. And this is how it's done. If I may, let's just do carbon. It's element number 6. We start filling the electrons in. I want to make a point with carbon. 1s2, 2s2, 2 electrons in the second s. We can only hold 2 electrons in the first s right here. So what do? We make another s. It's bigger and surrounds it. And then we fill that up. And then what do? Well, now we have room to put some of these p orbitals in there. So we do a px. This is px. This is py. And this is pz. So we do a px. The point I want to make is we don't put the second arrow in the first box. There must be 1 electron in each orbital before pairing. And the electrons have the same spin. So on both of these arrows, they're pointed up. Okay, for the next element, nitrogen, I don't put an arrow in one of the first 2 boxes. I put it in the third box. Okay. And then the next element, which would be oxygen, then I can put, if this were oxygen, I can put my other arrow there. Let me take that out. So, you have to, Hund's rule says, the lowest energy attainment electrons with the same spin is maximized. So, you put them in separate boxes before you put in an electron of the opposite spin. That's all. There's a shorthand for doing this. Once you get to a noble gas, instead of for lithium writing 1s2, 2s1, we write helium. That's not much of a savings, but imagine sodium with, is it neon? 1s2, sodium would be 1s2, that's full. Now we go up 1, 2s2. Now we can fit the p's. 2p6. Sometimes this 2 is written or not. And now we still, for sodium, have one more element, 3s1. Well, all of this is the electron configuration for neon. So you can just write neon instead of that. You can also do this by looking at the periodic table, but I want to make a point about several things, okay? So I'm going to have you practice writing these. You have a choice of writing it and figuring out from the table. For example, oxygen would be right here, okay? 1, 2, 3, 4. It would be 1s2, 1, 2, okay, like helium. 2s2, 2s2, and 2p, 1, 2, 3, 4. Didn't count the first one there. So 2p, 4. Okay? And these are superscripts. So let me be a little clear. 1s2, 2s2, 2p, 4. 2, 4, 2 and 2 is 4, and 4 is 8. Oxygen. is element number 8. Okay? And these shells, the d shells, the d orbitals, correspond to the transition metals. These down here, the actinides and lanthanides, right here, tend to be below the table, because if we draw our table this way, it would be too big. Okay? So, there are some anomalies. We always like to talk about chromium and what's the other one? The electron configuration that doesn't fit right, that teachers always like to use. But they've tried to simplify things, and the best thing to do is just look it up, not in the periodic table, but in a Flynn scientific periodic table of the elements, where they give you the electron configurations there. You can remember chromium and is it copper, but for some of the others, it's much more complicated. That's not where I want to go. Actually, I don't know where I want to go. I'm in the wrong place now, aren't I? Is it here? No. Let me go back to Google. And I don't have it with me now. But there are a number of elements that don't follow the actual rules. And, so many teachers like to think they know and understand how it works because chromium and copper are different. And it is true that you fill in the 3D before you fill in the 4S. And we have this thing called the off-bow filling chart that is part of the problem for why people don't actually teach this correctly. This gives us 6 electrons with the expected spin, with the same spin, okay? 6 more equivalent electrons, and even that's a gross simplification. If you want to know the truth, there are 20 different atoms that do not follow it, that do not follow the filling rules, okay? So some anomalies, 20 out of 118, 15, 20%, that's a lot of exceptions to the rule. Chromium, copper, niobium, molybdenum, ruthenium, rhodium, palladium, silver, lanthanum, cerium, gadolinium, platinum, gold, actinium, thorium, proactinium, uranium, neptune, curium, scandium has the expected configuration and yet doesn't fill like these charts they ask us to fill out. Okay? So, it doesn't fill in the right order. And I can prove that to anybody who wants to send their teacher who is dogmatic about this. I'm not going to give you a lot of assignment on this for several reasons. You need to know about electron configurations. You need to know how to look them up and answer a simple question. They will give you a lot of information, but the only electrons I really care about are the ones in the outer shell, because they're the ones exposed to the environment, the surface, the rest of the system, that are doing the important things that I want to talk about. That is bonding. And they're also the electrons that are lost when we form a cation, and they're the electrons that have to interact with the electrons that are added when we form an anion. And for those of you going on, when you take organic chemistry, you'll learn that carbon is so unique, not because it has the expected configuration of 1s2, 2s2, 2p2, because it does something called sp3 hybridization, and these 4 electrons occupy hybrid, identical, I won't say identical, but they occupy hybrid equivalent orbits. And so this configuration isn't even the configuration involved in carbon. And these electrons are going to be involved in bonding and form bonding orbitals that aren't the same as these electron configurations. They'll assume a new bonding configuration and new shaped bonding orbitals. So I'm going to give you a light assignment asking you to fill out and write some of these electron configurations. And after that, we'll move on to the periodic table. I want you to know that when people say, you need to know this because it'll tell you how to, you know, how to understand the periodic table. But these electrons come together in space to assume a stable configuration that accommodates all these electrons. And it is these atomic structures that result in the blocks of the periodic table. It's not the man-made periodic table that determines how these electrons go in. It's the other way around. And it is good to know and understand these things, but we're going to move on to explain how the arrangement of these electrons in atoms help us make predictions and explain why elements why elements behave the way they do. And the shape of the periodic table itself reflects these electronic arrangements of the elements. I know this is heavy. We'll move on to periodic properties and making some of those predictions in the next chapter. Look at this assignment. Give it a little bit of your time. Thank you for listening to this long lecture. But we've done with this chapter. Your assignment shouldn't take you more than half an hour. So remember, this would have been a week worth of lecture. If you were meeting on campus, we would be having 3 hours of lecture a week and another couple hours of lab, for which you would have a significant amount of work or assignment. So I'm sorry this takes a little bit of time, but we will just move through this so we can go on to periodic properties, and then our subsequent chapters in Brown and Lemay et al. Dealing with bonding and molecular geometry. Goodbye now. Let me stop